I'm going to talk to you about optimizing resource usage in Kubernetes. So I'm going to tell you a bit of what we've done on our product. So hopefully you'll get some ideas to things that you can do on your own thing. So before we start, anybody heard about Kubernetes? Just kidding. This used to be a question before, a long time ago. But who is using Kubernetes on production? Yeah, like who isn't, right? It's like AI now. Principal scientist, yes, greatest title ever. But I also use, I also created the Jenkins Kubernetes plugin. Who is using Jenkins on Kubernetes? Some people still using Jenkins, good. So what I'm going to tell you about is our product, a little bit of an introduction so you understand what the choices we made. So it's Adobe Experience Manager, which is content management system and asset management. And you may not hear about it because, of course, there's PDF, there's Photoshop, and other cool things that Adobe does, but it's used by a lot of Fortune 100 companies and a lot of enterprises, and you've probably seen it multiple times per day running some sites, but you didn't realize. So it's an existing distributed Java OSGI application using a lot of open source components from the Apache Software Foundation. We are very big into open source. And the interesting point also is there's a huge market for extension developers. So developers that will write code for AM, and we will run that code for them. And that's why this becomes interesting later on. We launched the AM cloud service. We're running on Kubernetes, and we are running on Azure Cloud. And we have more than 50 clusters growing because it's a content management. People want to have their content closest to their customers. So we run in every region possible, pretty much. So US, Europe, Australia, Singapore, whatever, and adding more regions. A particularity at Adobe is that we have a dedicated team that manages the Kubernetes cluster for multiple products. And as I mentioned, we have customers writing code that we run for them. And so we have to do a lot of permissions, checking, and ensure that their things are tight because we run somebody else's code. We use namespaces to provide the scope, network isolation, quotas, permissions, so we don't mix customers on namespaces. And the number of what we call AM environments, so each customer can get multiple AM environments, typically development, stage, production, but they can get more. This translates to three or more Kubernetes namespaces. And what I like to call it, AM is a micro monolith. So we run thousands of these environments. So we are taking the same similar application that was a lot of lift and shift from an existing application into Kubernetes. And we run this, I think it was around 20,000 of them. We are using init containers and many sidecars to apply this division of concern. So with the Java application, you have a bunch of sidecars, init containers that set up things without mixing, without having to change the AM application itself, the Java code. So this allows us to handle things like logging or several operations that are more infrastructural than application side. So for what you're here is more about the scaling on resource optimization. We have now, more than 17,000 environments. We have multiple teams building services. So we're looking for a lot of ways of scaling that are orthogonal to development teams. So yes, we can go to development teams and tell them, hey, change your code and change this, change that, so this works better in the cloud. But then that involves a lot of work from us, from the development team. So we're looking for ways to optimize this, also the infrastructure level, and this is what Kubernetes provides us. On the Kubernetes side, you have requests and limits. Everybody that was working with Kubernetes knows this. And requests is how many resources you have guaranteed. Limits, generally, this is how many resources can be consumed. That's the big picture. And these are applied to CPU, memory, and ephemeral storage. What happens when you go over your requests? And on the CPU side, you're going to end with CPU throttling. On the memory side, if you go over the limit, your container is going to be killed by the kernel or by the kubelet. On the ephemeral storage, the limit is enforced, and whenever you go over that limit, the pod is evicted and is started somewhere else as the typical scheduling cycle of Kubernetes. Now, focusing on the CPU requests and limits, anybody using Java and Kubernetes here? Just a few people. So we have some specific issues with Java. I'm not diving into Java too much because I don't have a lot of time here, but this applies also to other languages. It's just that Java is a bit particular about some things. So CPU requests are used for scheduling, but it's also interesting that they're also used as a relative weight. So it's not really the number of CPUs that can be used, it's a weight between the different processes once your container or your pod is scheduled. When you say, I want this resource or this container to use one CPU as a request, it means that it can consume one CPU cycle per CPU period. So if you only have two containers running on the same node, even if they have 0.1 CPU requests each, they can use up to 50% of the node CPU. So it's not a limit, it's not limiting anything, it's a weight after Kubernetes has done the scheduling. So first, Kubernetes goes and finds a node that has room for what you're requesting, and then second, once it is running, is a weight between processes. So CPU limits in Kubernetes, this translates to cgroups, quota, and period. The period is by default 100 milliseconds, and the limit is the number of CPU cycles that can be used in that period. If you go over that time, your container is throttled. So, for example, if you set up 500 MCPUs, M cores, in Kubernetes limits, that means you can use 50 milliseconds of CPU time per 100 milliseconds period. If you set 1,000, it means that you can use 100 milliseconds time per CPU period. This is a bit challenging for things that are multi-threaded by nature, like Java. So if you have 4 threads running on your application, and they are all consuming CPU, your container is going to consume all the CPU in just 25 milliseconds. And then it's not going to do anything for 75 milliseconds. So trying here in an example, a drawing. So you have one thread, it's using one core, that's fine. If you use all the CPU you can, you're going to run during the 100 milliseconds, you're going to be doing things. But if you have 4 threads and they are running on different cores, then you're going to be throttled for most of the CPU period. So this is something that got a lot of people off guard because, for instance, in Java, it's very typically multi-threaded, but that applies to anything else. If you get requests, you will see sometimes, the requests are typically processing this amount of time, which is fine, but now I'm getting spikes where the request time goes through the roof, and I don't know why. And that's what typically happens. Your container is getting throttled. On the scaling part, we are using a bunch of things together in order to at the end of the day, save resources and save money. Because when you want to do cool things, the best way to get them approved is to say, we're going to save money, right? We use the cluster autoscaler, increasing the cluster size based on how many resources you need to run at any point of time. We use it based on CPU and memory requests, the typical thing. And we also leave some headroom for spikes, so you don't have to go and get new VMs every time you have spikes. And we use multiple scale sets in different availability zones to have multi-AC to have some redundancy. When you are running at the scale, it can be easy to cause a denial of service because you are requesting too many things and you may be getting throttle on the API servers. But that's what we do. We set also the max node at the cluster level because we don't want, because we make a mistake or something, we don't want the cluster to grow indefinitely. We use the least waste scaling strategy, so to do the bin packing, and this just goes and tries to find the node group with the least idle CPU after scale up. So this is one. I think this is the typical way that you would set it up, and this provides us with savings of 30–50%. Right? We don't need to run the cluster at high capacity all the time, so it's a huge saving. If you see here in this graph, this is a typical setup on our cluster autoscaler. It goes up to, in this case, 100-something nodes and keeps going up and down depending on the number of requests, and which translate on CPU usage, memory usage, and so on. And in this graph, you can see how a bug here caused this to quickly go through the roof to the max limit of nodes. So I think that's why it's important to have a max number of nodes, because if you make a mistake, then you don't want it to grow indefinitely. Once the bug was fixed, then things went back to the normal. The other autoscaler we use also for in the Kubernetes ecosystem is the vertical pod autoscaler, which is increasing and decreasing the number of resources for each pod. So one thing that was very annoying with VPA, and well, it still is that it requires a restarting of pods. So every time the VPA says, oh, I think this pod should have more resources, or I think this pod should have less resources, those recommendations do not apply until that pod is restarted. And you can configure it to be restarted automatically or to be applied on the next time the pod starts, or a pod in the same deployment starts. But on 127, Kubernetes 127, VPA in place, what's called in place recommender or something like that, is now alpha, and you can configure it so it changes the resources on the fly without having to restart the pod or recreate the pods. Before that, VPA makes it is slow to respond because you need the pods to be restarted, and depending on how much time your pods take to start, that may negate the benefits of having VPA. And if you don't want random pod restarts, don't set it to auto, because auto is going to say, oh, I think this pod should have a different number of requests or limits. I'm going to just kill it. So you don't want that. Probably. There's use cases for everything. We only use it on development environments, or used it in the past on development environments to scale down if not used, and only for some containers. And on the Java case, the JVM footprint is also hard to reduce, right? The JVM Java use case is when the JVM starts, it grabs all the memory that you set the heap size to, and then it's not. Kubernetes doesn't know anything about how much memory is actually used in the heap because the Java process grabs it all. So that's what makes Java particularly hard. And they save us like a 5%, 15%, something like that. We also use the horizontal pod autoscaler, which allows us to create more pods when needed. This is the typical one, scale horizontally. And what we do is scale on CPU and HTTP requests per minute metrics. There's always advice to not use the same metrics as VPA, as both can conflict with each other. CPU autoscaling, in our case, was a bit problematic because if you have some tasks that run, let's say, some background job, something like that run on each instance, on each pod, adding more pods doesn't help, right? So if you start more pods and those pods start doing background tasks, and then you start another pod and it keeps doing that, then you are just scaling forever, and it doesn't solve any problem. And also on the startup time, when you have init containers or a Java application at a startup is very CPU hungry, that may cost autoscaling to kick in just temporarily, so you have to balance this out also. So maybe you start another pod, and then Kubernetes sees the CPU spiking, and then it starts another one, but then the spike goes down again, and you are just thrashing pods, just creating and destroying pods, which may be a problem or not, depending on the case. On our case, because we also are warming up the cache on a startup, RPM autoscaling is better suited, and as long as customers don't have expensive requests where they need a lot of CPU. And this saves us a lot of requests, because 50-75%, because we are continuously going up and down on the number of pods. So on pods, so this is the number of pods on the top, the RPM, requests per minute, at the bottom, and this is what it looks like on our typical day. When to use VPA, HPA, depending on your use case. In Java, for instance, increasing the memory and CPU is more effective than adding more replicas, because you get more bang for the buck, and the Java footprint is a bit big, and if you have a big application, it's even bigger. But I mean, you're going to need multiple replicas anyway if you want to have high availability, so this is the balance that you have to play with. If you have a new build from scratch microservice that scales horizontally great and has very low footprint, then you may go with HPA. HPA is going to be the better option. The other thing we did is, who is using ARM here? Just very little, a small amount of people. For us, we are making around 15-20% cost savings for the same performance. And it's in a container world, this is very easy to do. You just configure Kubernetes, create to use a new node pool with ARM machines, and you start playing with the tolerations and the pod, what's called the SKUs that you want your pods to be. No, it's not the SKUs. The SKUs is for HA. But you're basically saying to Kubernetes, oh, I want this workload to use ARM if available, or I want to use always ARM. And with multi-arc Docker images, it's very easy to do. Especially for Java. Java, you have plenty of Java images for different architectures, and you just switch one for another, and it's all transparent. You don't even need to recompile things. One thing that is not on the Kubernetes ecosystem that we built ourselves was hibernation, which is scaling down to 0 for environments that are not used. We have multiple deployments that are associated with an AM environment that we scale down if there's no request incoming for a period of time. And this is for sandboxes that we call development environments, things like that, either internal or customer. What we are also doing is deleting ingress routes and other objects that may limit the cluster scale, because at some point, maybe CPU and request is not your limiting factor. In our case, we have the limiting factor is the number of objects we have, the number of watches, the number of memory the API is consuming. So not only we are scaling down the number of pods, we are also removing objects from etcd. We built it in a very easy way. It's a job that checks for Prometheus metrics. If there's no activity in in X number of hours, scale down the deployment to 0, and then the customer is shown a message where they can click and say, I want to hibernate this. Now there's other options out there like Knative where it would allow you to do this more automated, which is more like function as a service with Knative. But in our case, the JVM takes like around 5 minutes to start, so that's a bit hard to do automatic hibernation, and this saves us a lot of money, because there's a lot of development environments, there's a lot of engineers working on things that they don't need to use all the time. So, and today, you could easily do, or more easily, do this sort of hibernation with Keda. Keda is a Kubernetes-based event-driven autoscaler, and you can use a lot of different types of events to scale up and down your workloads. So if I were to rewrite hibernation today, I would probably use Keda, if I cannot go with Knative or something more function as a service. So Keda allows you to do scaling on number of events on Kafka or on a cron schedule, any events from cloud provider, and also very interestingly, Kubernetes workloads. So if you have multiple deployments that are somehow related, and you say, every time this deployment scales down, I want to also scale down all these other things. So you could have supporting deployments or services being scaled down when another deployment is scaled down. Other scalability concerns. So this is all the basic CPU, memory, request, limits, things that everybody looks at. On our case, we also hit limits on etcd, right? Kubernetes is not a database, although a lot of people use it like that. We do. So you don't have an infinite capacity of things to store. All the YAMLs you create, those end up stored in etcd, and the limit is around 8 gigs. And trust me, you can reach that limit, and things are not pretty. etcd every mounted object will also create a watch. The number of watches increase the memory usage on the API. This slow response time from the API will also cause API requests to timeout. They time out at 1 minute. And then when the API is not answering, you are you're having a bad time, because nothing in the cluster will be able to react. You're not going to be able to do kubectl commands. The autoscaler is not going to be able to scale up the number of pods. If you need to schedule, if a pod gets deleted, a new pod is not going to be able to be created. It's not a good place to be. And it's better to create less objects with more data than too many objects, also because of the watches, but also having to account the 8 gig limit. When you get to close to the limit, or you hit the limit on etcd, etcd becomes read-only. And that's also not a great place to be, because nothing can be updated. If you want to avoid watches, you can use immutable secrets and config maps, and this will not incur at the cost of a watcher, but it will also not update the mounted files in the pod. So again, don't use etcd as a database. That's my advice. And another one that we realize is the max pods per node. The default is 110 pods per node. If you have big nodes and small pods, this is a lot of waste. So we increase this to 200 something, and we reduce the cluster size quite a while. And that's something that's fairly easy to do. I mean, you're going to have some other concerns about the networking because each node needs to have enough IPs for all the pods and so on. But that's another thing that you can do. So to sum it up, before you can go to lunch, there's a bunch of things that my idea for you is so you remember, there's a bunch of things that you can do from the application side, tuning CPU, memory, garbage collection in Java. But from the Kubernetes ecosystem, you can use the cluster autoscaler, HPA, VPA, KEDA, all these different things. Open source, they're there, free. And you can do this resource optimization at both levels. And having a combination of both will help you improve the resource usage of your clusters. So if you have any questions. Yes.
Maybe first a round of applause. Yes. We do have a couple of questions, actually.
Okay.
So let's go. All right. So there's been more than one question about, are you setting CPU limits?
Oh, that's a great question, because we are setting CPU limits, but I think we shouldn't be setting CPU limits, and we are doing this debate. For production workloads, it's better to not use CPU limits in a lot of cases, because the weight, what I was mentioning about the request is a weight. So removing the limits, the only thing that allows you the pods to do is to use CPU that is available and unused. So for production, yes, you should probably remove the limits. For other environments, maybe you want to keep the limits because, let's say, in a stage, maybe you want to limit in a stage and not limit in production, because otherwise you may end getting better performance in a stage that you get in production, depending on which node your pod is running on. But yes, removing limits in production, CPU limits, it's a good thing to do, typically.
It's a good thing to do. Okay, good. All right, so let's pick another question. Let's go for this one. Are you using eBPF for real JVM app memory usage monitoring?
Not eBPF, not yet.
Not yet?
We use eBPF through Cilium to other things, but not for that.
Excellent. Do you implement a node autoscaling, and how?
Yeah, node autoscaling we use the cluster autoscaler to scale up and down based on it's the Kubernetes node autoscaler. We are also looking at Carpenter. It's another autoscaler that will allow you to do more fine-tuning.
Perfect. There was someone very disgruntled saying, you didn't mention Carpenter. Okay, so now he mentioned Carpenter. Done. Perfect. All right, let's see. All right. When VPA kicks in, will the pod also be rescheduled to another node if necessary?
Yes.
These are very short questions and answers. This doesn't give me a whole lot of time to read all of the ones in review. Thanks, y'all. You could have said, like, it depends, and then make up a longer answer.
It depends. If you use the one that requires the restart of the pod, yeah, the pod may end in another node. If you use the in-place alpha thing, I'm not sure how. You gotta be careful because you cannot in place just increase all the memory you want forever, right? The node is gonna hit some limits. You're not able to increase, only decrease? I thought you could increase, but I don't know. I haven't tried yet, but it's in the to-do list with all the other things.
With all the other things, yeah, okay. Let's do maybe 2 more questions. Can we deploy IAM on our own Kubernetes infrastructure?
No. No.
Is that a not yet? Or?
No, I'm not here to talk about selling products, but we run it for you so you don't have to go through that. We manage everything for you. It's great.
It's great. Okay.
Yeah, especially for you.
Yeah. I love that. You're not selling anything, but it is great.
Yes.
Okay, good. All right. What else? Let's do this one. Would Kida be a good candidate for hibernating pods based on Prometheus metrics?
Yeah, I think so. Yeah. Yeah. I mean, maybe a bit overkill because, you can use HPA. Well, HPA has the option of scaling to 0 using metrics, so maybe you don't need to go to Kida to do it, but yeah.
But yes.
Yes.
Yes. Okay. Yes. Excellent.
I'm in Germany. I was told it's like short answers to the point, and
yeah, exactly. Maybe you need to just answer or ask better questions, like in how far could you do blah 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 blah. Then we get longer answers.
That's what AI is for.
Yeah. All right. Perfect. I think we're going to break for lunch. I just want you to know that we'll do a overflow room here for the session by Kelsey later on. So don't feel like you already need to reserve a seat in the main room for a Kelsey session. You can also just comfortably sit here and watch the overflow screen. Yeah. There's not going to be any live questions. There's also going to be Slido questions. So you win nothing by sitting in a very, very overcrowded room. Yeah. Just join us here. Let's give it up for Carlos one more time.
Thanks.